Okay, so today's video, we're continuing to look at sketching parabolas. So over the previous two videos, we first of all looked at sketching a parabola when the equation is given in turning point form. In the video after that, we then looked at sketching a parabola when the equation is not given in turning point form, but we then did that by converting to turning point form using completing the square. Today we're going to be looking at when we've got the equation not in turning point form, but how we can sketch it without having to convert it to turning point form. Okay, so I'm not saying the previous method was a bad method. In fact, in many cases I think it's a really good method for sketching the parabola. But there are other options too, particularly if the equation factorizes. The example we looked at in the last example of the previous video, that equation wouldn't have factorized, didn't have any solutions, didn't have any x-intercepts, and so therefore the method we used in completing the square to turn it into turning point form was actually probably the method of choice. Okay. All right, so what we want to look at today is, rather than focus on finding the turning point first, let's instead focus on finding the x-intercepts first. X-intercepts meaning we let y equal 0 and we solve for x. So we have a quadratic equation to solve. When the equation's in turning point form, we don't need any particular quadratic methods, we just do the same thing to both sides until we get x on its own. When the equation's not in turning point form, when it's in this general ax squared plus bx plus c form, we need to use our other quadratic solving techniques, so attempting to factorize and then use the null factor law and or using the quadratic formula. We'll talk about the quadratic formula in the next video. So what we want to look at today is examples where the quadratic does factorize. So rather than worrying about completing the square to find the turning point, let's focus on factorizing to find the x-intercepts first. And then from the x-intercepts, we'll find where the turning point is. Okay, so we want to talk about that process first. So I'm going to skip some steps in this first example here and say to you, okay, the graph of y equals x squared minus 6x plus 8 has x-intercepts at 2 and 4. Okay, now we can find them, that's fine, but I'm not focused on that right now, we'll do that in a bit. But if I know that I have a parabola with x-intercepts at 2 and 4, I want to find the coordinates of the turning point using that information. So having found the x-intercepts, how do I then get to the turning point? Okay, let's think a bit about this graph, what we know about it so far. So the fact that this is a positive x squared term tells me that I have a happy parabola. Okay, plus 1x squared, so positive coefficient of x squared, the shape is happy. Okay, and we have x-intercepts at 2 and 4. All right, so let's think about what that looks like. Just a rough sketch. We don't know everything right now, obviously. So 1, 2, 3, 4. We have a parabola that goes through the x-axis. In fact, let's just move that down a little. Didn't think very well properly about that scale. Okay, so let's think about our parabola is going through here, and it's happy. So something like that. Okay, that's x equals 4, and that's x equals 2. Alright, so we want to use this information to find the coordinates of the turning point. So what we need to utilise here is the fact that the parabola is a symmetric shape, and the x-coordinate of the turning point, or the axis of symmetry, will be halfway between the two x-intercepts. So the axis of symmetry is going to have to be at x equals 3, which is halfway between 2 and 4. If we want to think more generally about how do we find a number that's halfway between two numbers, obviously it's really easy here. We can see that halfway between 2 and 4 is 3. But what if my x-intercepts were at 7.8 and negative 15.3? Okay, so to find halfway between any two numbers, we simply add them together and divide them by 2. We average them. Okay, so our x-coordinate of the turning point is 3. So now what we know is that that point has coordinates of 3 something. Okay, so then the next thing is to think about, well, how are we going to work out the y-coordinate of the turning point? So let's think about what this graph is. This is the graph of y equals x squared minus 6x plus 8. Remember, the graph is every single pair of numbers, x values and y values, that fit this relationship. So what we need to work out here is, we want to know what is the y value when x is equal to 3. So we put x equal to 3 into the equation so that we can work out what y is. Okay, so we know that the turning point happens when x equals 3. And then we want the y coordinate of that point, so we want to know what does y equal when x equals 3. So that's going to be 9 minus 18 plus 8, negative 9 plus 8, so negative 1. And so therefore, the turning point has coordinates of 3, negative 1. Okay? So in this process, we want to focus on finding the x-intercepts first, from those x-intercepts then being able to find the turning point. Okay, so let's have a think about example 2 here. So sketch the graph of y equals x minus 6 times x plus 2, labelling the turning point and all axis intercepts with coordinates. Okay, so in that factorised form, the quickest thing we're going to be able to find here is the x-intercepts. So the x-intercepts are going to be when y equals 0, what does x equal? And the fact that it's already factorised means it's very quick and easy for us to find here that this means that x minus 6 has to equal 0, so x equals 6, that's using our null factor law, or x plus 2 equals 0, and so x equals negative 2. So our x-intercepts are at 6 and negative 2. So from here we're going to focus on finding our turning point. Okay, so the turning point, the x-coordinate, will be halfway between these two x-coordinates. So we're going to add them together and divide them by 2. 6 plus negative 2 is 4. 4 divided by 2 is 2. So the turning point happens when x is equal to 2. And then we need the y value when x equals 2. So we substitute that into our equation. So 2 minus 6 is negative 4, multiplied by 2 plus 2, which is positive 4. And so the y coordinate, is at negative 16. So turning point is at 2, negative 16. Y-intercept, we find by letting x equal 0. So it's going to be 0 minus 6 times 0 plus 2. So that's negative 6 times 2, so negative 12. And so we've got our two x-intercepts, our turning point, and our y-intercept. We can think as well about shape. The fact that if we expanded this out, we would have positive x squared means that we have happy shape. Okay, and that marries together with where we found the coordinates of the turning point to be at 2, negative 16. Okay, let's think about suitable axes. All right, 1, 2, 1, 2, 3, 4, 5, 6. So x-intercepts at negative 2 and 6. Turning point at positive 2, negative 12. Sorry, negative 16. Okay, so that's negative 16, which makes that negative 8, 4, 12. So y-intercept's going to have to be there. Again, I'm just going to draw myself a symmetric point somewhere around about here, just to get my shape nice and symmetric. Oh, sorry, I hit the edge of the computer. Try that again, I'm going to come the other way. Alright, so we've got 6, 0, negative 2, 0, 0, negative 12, and 2, negative 16 for our turning point. And so we have our completed parabola with all intercepts and turning point marked. Alright, example 3. Sketch the graph labelling the turning point all axis intercepts with coordinates. Okay, so our equation is written slightly out of order, so let's perhaps just rewrite it to be clear about what's happening here. So it's negative x squared plus x plus 6. So straight away I can tell that my shape is going to be sad because of the negative x squared. Okay, so we're going to have a sad parabola. Let's think about our x-intercept. Well, actually, let's do the y-intercept because that's nice and easy from this form. So y-intercept, when x is 0, y will be 6, and so it's 0, 6. Let's find our x-intercepts first. We don't have turning point form, so we'll find the intercepts first if we can. So 0 is going to be equal to negative x squared plus x plus 6. Now, factorising a non-monic quadratic is quite difficult. Well, it's more difficult than a monic one, but we can very easily make this monic. We can think about adding everything onto the left-hand side of the equation or multiplying both sides of the equation by negative 1. Either way, what happens is we get positive x squared minus x and minus 6 equals 0. So we're looking to factorise the left-hand side. It's a simple quadratic. Factors of negative 6 that add up to negative 1. It's going to be minus 3 and positive 2. And then we use our null factor law that says if two things multiply together to equal 0, then one of them or both of them must be equal to 0. So x minus 3 must equal 0, or x plus 2 must equal 0. So x equals 3 or x equals negative 2 are my two x-intercepts. Okay, then we're going to need our turning point. Sorry, a bit cramped for space here. So we've got our turning point is going to be halfway between our two x-intercepts. So we're going to add them together and divide by 2. 3 plus negative 2 is 1. 1 divided by 2. So our x-intercept is at 1/2. Sorry, the x-coordinate of our turning point is at 1/2. So then we need the y-coordinate of the turning point. So we're going to substitute that into our equation. So negative 1/2 squared plus 1/2 and plus 6. Now I know some of you might not like fractions and might not like that there's fraction work required here, but even if we had completed the square here, completing the square would require fractions as well. We do similar fraction work as well because the turning point has coordinates that involve fractions. Okay, so it's not going to be avoidable by choosing a different method. Right, half squared is a quarter, so we've got negative 1/4 plus 1/2 plus 6. Let's get a common denominator. Minus 1/4 plus 2/4 plus 24/4. So that is going to be 25/4. So our turning point has coordinates of 1/2, 25 on 4. So 25 on 4 being just a bit more than 6, just as a sense of where things are. Alright, so let's draw in our parabola now. We've got our turning point, our y-intercept, and our two x-intercepts. So let's think about what we need. Sorry, let me just... Okay, 1, 2, 1, 2, 3. Now, our y-intercept is at 6. 1, 2, 3, 4, 5, 6. And our turning point is at 1/2, 25 on 4. Now 25 on 4 is 6 1/4. So it's just higher than our y-intercept. Think about the symmetry. So we're going to have another point sort of there as well. So through your y-intercept, turning at your turning point, through your symmetry point. A bit of a wobble there, let's try that again. My symmetry point's a bit close, that's why. Struggling, should have stuck with the first one. Okay, so y-intercepts are 3, 0, negative 2, 0. Sorry, x-intercepts. Y-intercept is 0, 6, and our turning point is at 1/2, 25 on 4. And there is the graph of our parabola. Alright, example 4, the final example. Sketch the graph of y equals 2x squared plus 3x minus 2, labelling the turning point and all axis intercepts with coordinates. I suspect I might not have given us enough room here again. I should have given us a full page for these last two. So write a bit small as you do it. So sketch the graph. So let's focus first of all on thinking about the shape. So we know the shape here, positive 2x squared, happy shape. So the graph goes this way. Y-intercept is nice and easy in this form, so let's do that first as well. Our y-intercept will be negative 2. By the time we let x equal 0, we'll get y equals negative 2. So that is 0, negative 2, coordinates of the y-intercept. Let's focus on our x-intercepts. So we'll let let y equal 0. Okay, so we want to see if we can factorise this. So remember, non-monic quadratic, so anything other than 1x squared. We have a more complicated process. 2 times negative 2 is negative 4. Factors of negative 4 that add up to positive 3 are positive 4 and negative 1. And then we rewrite 3x squared as plus 4x minus 1x. Or you could do it as minus 1x plus 4x if you prefer. Okay, so we use the numbers that we found as factors of -4 to break up the middle term. Now we're going to use factorisation by grouping. Common factors in the first two terms, 2x times x plus 2, and then looking at the second two terms, common factors there, -1 times x plus 2. We know we're on the right track because the brackets are the same. So x plus 2 becomes the common factor, and when we take that out, we get left with 2x minus 1. Null factor law, two things multiplying together to equal 0, says that one or other or both of them must equal 0. And so we've got x plus 2 equals 0, so x equals -2, or 2x minus 1 equals 0, so 2x equals 1, x equals 1/2. So there's our two x-intercepts. Alright, so we then need our turning point. Yes, we definitely don't have enough room here. My apologies. Hopefully you're able to write small or find a blank space somewhere to add your graph in. So our turning point is going to be halfway between our two x-intercepts. So we need to add them together and divide them by 2. Now, because one of them's a fraction, I'm going to write that slightly differently. So I'm going to add them together, -2 plus 1/2, and divide them by 2, rather than have a fraction in a fraction. Okay, so -2 plus 1/2, so that's -2 is -4 on 2, plus 1 on 2, so that's -3 on 2. And then we're dividing by 1/2, dividing by 2, which is the same as multiplying by 1/2. So it's -3 on 4. Right, then we need the y coordinate of the turning point, which means we need to substitute -3/4 into our equation to find what does y equal when x equals, -3/4. Okay, so that is 9/16, -3/4 squared. This is 3 times -3, so it's minus 9/4 when we multiply 3 times -3/4. And then minus 2. Alright, again, rather than do 18 on 16, let's cancel the 2 down with the 16. So it's actually going to be 9 on 8. Let's get a common denominator here. So that's minus 18 on 8, and then minus 16 on 8, the 2. So 9 minus 18 is -9, and minus another 16 is -25. So our turning point has coordinates of -3/4, -25 on 8. Okay, so we've got all we need, our y-intercept, our two x-intercepts, and our turning point. And again, apologies for the lack of space here. So x-intercepts at -2 and 1/2, y-intercept at -2. Let's think about 25 on 8. So what's that? -3 1/4. Sorry, -3 1/8. So a bit more than 3, just in terms of thinking about where that point is. Alright, so -2 and +1/2. Sorry, where was the y-intercept again? -2 as well, so just thinking about how to draw my axes. Okay, 1, 2, 1, so that will be 1/2. In fact, I might make them bigger, sorry. Let's go with 1, 2. And so that's 1, and so that's 1/2. 1/2 and -2 are my two x-intercepts. My turning point was at -3/4, which if that's -1/2, that's -3/4 there. So it's going to be somewhere down here. If we make this, let's put the turning point here, for example. Okay, remembering that's a bit more than 3. So let's make -2 there for my y-intercept about there. A symmetric point somewhere over here, just a rough dot in space, just to give me a sense of where I'm aiming. I missed it slightly, but that's okay. Okay, so that's the point 1/2, 0. That's the point -2, 0. This is the point 0, -2. And that's my turning point at -3/4, -25 on 8. Once again, I've got my x-intercepts, my y-intercept, and my turning point, and there is my completed graph. So exercise 7c today, I don't want you to complete the square for these. I want you to focus on using the process of factorisation to solve to find the x-intercepts, and then once you've got the x-intercepts, being able to find the turning point from there. I'll link somewhere in this video as well to the previous video or videos on factorising quadratics. Again, if that's a skill that you are not confident with, that's something you really need to be working on.